divide by the standard error of 0.19, and we know that our outcome, our sample mean, is 3.16 standard errors below the mean. So that might seem like a lot right off the bat. 3.16 seems significant, but we need to do one of two things to make sure. One, we need to get a p-value, or two, we set up our critical values and determine what we would mean by extreme. For this question, we'll set up critical values. So if we want a 5% significance level, that means there's going to be 2.5% in each tail. And what do we need to do with the degrees of freedom thing?
Subtract by 1.
Yep. Yep. Sample size minus 1. Sample size is 10. 10 minus 1 is 9. So we have 9 degrees of freedom. We look on the t-distribution. And if we have 5% significance level, that's going to be 2.5% in either tail. So what is that, Brian? 9 degrees of freedom, 2.5% in the right tail.
2.262.
Fantastic. So those are our critical values. Plus or minus 2.262. So if we find a z-stat that is greater than 2.262 or more negative than negative 2.262, that would be highly unusual given that the true population mean is exactly 25 hours. So we did find something that was highly unusual, so we reject the null hypothesis. Any questions at all? All right, let's do quiz 5. So quiz 5 is just hypothesis testing with proportions, mean differences, and proportion differences. All right, we already know hypothesis testing, we already know proportions, we already know proportion differences and mean differences, we just put them all together. Alright, so question 1. So in past years, at least 20% of students at State U chose to pursue public service careers after graduation. So State U has a reputation of at least 20% of students going into public service. For an editorial piece on declining student commitment to public service, the school newspaper surveyed a simple random sample of 400 currently enrolled students and found that only 56 of them expressed an interest in a career in public service. All right, 56 out of 400, what percentage is that? 14%. Yes, is that at least 20%? No. Okay, so what do we think? Has, if say the administration claims that at least 20% of our students are going into public service, what do we think so far? Right. We're not quite ready to reject. We're suspicious. Okay, we're like, all right, we're disinclined to believe you at this point, but let's investigate further. Does this sample result, because it's only a sample, provide statistical evidence of a decline in student commitment for the population of all students enrolled at State U? That is, can the sample be used to reject a true population proportion greater than or equal to 20% null hypothesis? Use a significance level of 5%. All right, so they actually tell us the null hypothesis they want. So look in the answer, you see that true population proportion greater than or equal to 20%. How many ways are there to disprove this null hypothesis? One way. It would be a test statistic significantly lower than 20%. Like if this editorial piece came up with 28%, or 29%, or even 40 or 50%, those would all be greater than 20%. So you'd be like, oh yeah, at least 20%. That's all the null hypothesis claims. So we found some evidence to the contrary, we just determines, to be determined whether it's overwhelming. And if it is overwhelming, we reject that and assume the alternative. So our sample proportion, as we stated, is 14%. The real question is how many standard errors below the mean, or the assumed mean of 20%, that would be. Well, so let's calculate our standard errors. Remember, for proportions, we just use the formula for standard errors when we get to the sampling distribution of the sample proportions. It is the proportion, the assumed to be true proportion of 20%, times 1 minus 20% divided by the sample size. Take the square root of that whole thing, and we get 0.02. So 2%. So how many of those is our test statistic? Alright, well, if you go down one line, you see the difference between 14% and 20%. That's 6% difference. So that is 3 standard errors. 3 standard errors below the mean if the claim of 20% is true. 20% or more, at least 20%. So in this question, we're actually asked for a p-value to calculate the p-value. So if what the administration says is true, at least 20%, what is the likelihood that our sample of 400 came out to be 3 standard errors below the mean? How do we find that out?
That's a good question.
I was just about to ask you, Brian.
I was struggling with the p-value.
Well, we look on the z-table.
On the z-table?
Yep. Alright, look for a z-value of -3.
Say that again?
Yeah, look for a z-stat of -3. And what is the probability associated with a z-stat of -3?
0.0013.
0.0013. So that means the probability of having a z-stat of -3, this contains 0.0013, also known as 1/10 of 1% of the data.
Right, but our z-stat in this question is -2, right?
-3. Are you looking at your quiz or something? Yeah, your quiz is different. The z-stat for this calculation came out to -3. Yeah, there's one. This version of the quiz is -3. So, what would be the probability for -2? So let's not do that. Let's just assume -3. Let's not make it confusing. So -3, there's 1/10 of 1% of the data would be below that. So that means the 1/10 of 1% chance of getting a test statistic this extreme if the null hypothesis is true. That's a little unlikely for our tastes. So what do? Reject. Reject the null hypothesis. All right, we're good. Moving on to the next one.
So, but that was the end of number 1, failed to reject? Or are we on 2?
We're on number 1, we reject it because Brian told us that the probability of getting a z-stat of -3 is 1/10 of 1%, 0.0013. So that is
Oh, he has a different.
the z-stat is -3, right? It's on this. It's -3. We all good with that? If you happen to have your quiz open, it might be different than that.
Yeah, that's it. I have my quiz open, sorry.
Okay. Yeah. All right. All right. We're good? All right. Fantastic. Okay. So this one, Suppose we're working for the Canadian Agriculture Ministry, and we're testing out this new mix pesticide, and we want to know if it's making more money. So an agriculture study done to examine the impact of new pesticides in the Canadian canola crop. We take a sample of 459 farms using the new pesticide and a sample of 295 farms using conventional pesticide mix. And we find the average gross revenue per acre in the sample of the new mix farms was 155, and the average gross revenue per acre sample on conventional mix farms was 152.10. So, based on that data, what do we, the agriculture ministers of Canada, what do we think about this new pesticide? Sucks. Who said sucks? You said. Well, do we like more money? Do you like money, Brian? We like money, right? Everybody likes more money. So don't we like the one that makes us more money? I mean, we're not too concerned about cancer or any of that, right? Suppose we have suppose it's like a green pesticide, no harm to anyone. But maybe it's costing us a lot of money because we need to pay somebody for this or something like that. So we need overwhelming evidence that it is actually making us more money. Based on this sample, it says it's making us some more money. But is it in reality? Because this is only 459 farms or 295 farms. And how many farms are there in Canada? Canada's a big country. Maybe hundreds of thousands, I don't know how many farms there are in Canada. So let's construct a one-tailed hypothesis test. Let's actually just let's turn at this point to how we're going to set up this hypothesis test. If you turn the next page, so we probably would want to prove the hypothesis that the new pesticide mix is making us more money than the old pesticide mix. So that would be the alternative hypothesis. The mean in the population of new farms using the new mix minus the mean in the population of farms using the old is greater than 0. So that's just a fancy way of saying what? That the new mix is making us more money. The new mix is bigger. So if the new mix revenue is higher, then the new minus old is going to be greater than 0. Alright, so that's what we're setting up as our alternative hypothesis. And the reason we might set it up that way is because we want overwhelming evidence to prove that. So we're going to assume that it's not with the null hypothesis, and then we're going to have overwhelming evidence possibly to reject the null hypothesis, and boom, voila, we've got overwhelming evidence to prove that the new mix is making us more money. Now, like I said, for the final, it will just be versions of these questions. So you won't have to set up the hypothesis test, I don't think. You might want to, it's good to just have an understanding of it so you can check if your answer makes sense. But, you won't have the pressure of setting up the hypothesis test yourself. But just in terms of understanding it, that null hypothesis, the new minus old less than 0, what does that mean? New minus old less than 0, what?
It means that the old is greater than the new.
Yeah, the old is greater than the new, or equal to. So, yeah, and we don't think that's true, but we're just testing that hypothesis and see if we can reject that. Alright, so we have some evidence that the new is greater than the old. The question is it overwhelming evidence? So, in terms of the difference, let's go down to the test statistic. You see that test statistic? That's the 155 minus the 152.1. So that's a difference of about $3. Alright, we want to know how big of a difference that is. So we're going to divide that by standard error. And if standard error is really small compared to that, then it would be a huge difference. If standard error is really big then compared to that, then it would be a small difference. So let's figure out how we calculate our standard error. So let's go up a couple lines. And there we say the standard deviation of the sampling distribution of the sample mean difference is the formula. We have a formula for standard deviation of the sampling distribution of the sample mean difference. It is standard deviation 1 squared divided by sample size 1 plus standard deviation 2 squared divided by sample size 2 square root the whole thing. And we come up with a standard error of 5.586. Alright, so back to our test statistic. A point difference of $3, close to $3, $2.90. But the standard error is 5.8. So that $3 only amounts to 1/2 of one standard deviation. So it's great that the new mix is better than the old mix in our sample, but that's only 1/2 of one standard deviation above. So is that highly unusual? Is it enough to reject the null hypothesis that either they're the same or in fact the old is even better? It is not. It is not. Specifically, because we want to find the p-value for this test, we calculate the probability of getting a z-stat of 0.495. And the answer to that probability is 31%. So there's a 31% chance of getting something that extreme if the null hypothesis is true.
Where'd you get that 31% from?
Alright, so the 31%, we get it just right off the z table, right? We look for a test statistic of 0.495. If we look at the positive, we would have to do a 1 minus deal. Or we could look straight at the negative, negative 0.495. What do you see when you look at negative 0.495?
0.3121.
Yep, 0.3121. I think this one I used Excel,
Okay.
so I got 0.3103. And the reason, so you looked at the negative, and that just gave you the answer right there.
Okay.
You could look at the positive and do a 1 minus deal.
Okay.
You do not need to double that 0.3103 because this is a one-tailed test. There's only one way to disprove this.
Is that a rule that if it's a positive, the 1 minus?
If you look at the positive
that's-
table.
Yeah,
Okay.
yeah, the positive, well, alright, yeah, I didn't,
Because
go
the
ahead.
z-stat was positive 0.495, right? In this,
Yes.
so are you saying that because it's a positive value,
Yes,
if we want to use the z-table,
yes,
and we go and we look at the z-table here, because it's positive value, we have to say 1 minus 0.495.
we do, because the table gives us cumulative.
Uh-huh, okay,
So, what we're interested in is this amount here.
okay,
What it would be,
So I think that the best way to think of it is, look at the positive and say, well, if this up through here is, 70% or 69%, then this is 31%. That's the
Okay.
answer.
okay.
The reason why the negative works as a shortcut
Mhm.
is because the normal distribution is perfectly symmetrical.
Okay. So with the positive 0.495, you just look to say, what's the negative version of that? Like, we'll just go over here and we go to negative 0.4 and then go all the way over to that 0.09 column. And you did it on Excel, but I mean,
Yeah,
close enough.
yeah.
Okay, okay.
It's a one-tailed test, we don't need to.
Yes, you're correct, you're absolutely correct, Susan, it's a one-tailed test, we do not need to double it.
Or,
The question was asked just reading the Z table. How do we do it? And I think the best answer, to make sure we don't confuse ourselves, is look for positive 0.495, and it will tell us 69%. And so we know the answer we're looking for is 1 minus 69%, 31%.
okay,
What Dan was asking is there a shortcut just by looking at the negative side?
Mhm.
There is a shortcut just by looking at the negative side.
because they're perfectly symmetrical, you just, they're gonna be the same.
Exactly. All right, excellent. Now why don't we take 10
Yeah,
and we'll come back. And this is really, I think this is the hard part. Once we get to quiz 6 and 7 and 8, it's easy. So let's come back at 8:01.
149.